time you want to use for your presentation, but it will be nice if you have like at least 5-10 minutes for the questions. Most of the time, people write on the question and answer thing. I will also try to help you with the questions. I started time you want to use for your presentation, but it will be nice if you have like at least 5-10 minutes for the questions. Most of the time, people write on the. So I started YouTube streaming, as you might have heard. Shall we start? Let me introduce you very briefly. I'm sure you will have a slide on this as well. Good afternoon, everybody. My name is Zeki Erkin from Delft University of Technology. I am organizing this webinars on behalf of IEEE Signal Processing Society, particularly for the Information Forensics and Security Technical Committee. And this is our fourth webinar and the first one after the summer break. So I would like to welcome Professor Anderson Rocha from University of Campisi. Anderson, thank you very much for being here. And your talk is very on a timely and important topic, artificial intelligence and digital forensics. I would like to give you the floor, and I hope you can also talk about yourself in more detail.
Okay, thanks, Zeki. So, good morning and good evening, everyone. I know that we have people from all over. So I'm Professor Anderson Rocha, and I'm the coordinator of the Artificial Intelligence Lab called RECOD AI here at the University of Campinas, Brazil. And as a first thing, I invite you to follow us on LinkedIn. You can quickly look for RECOD AI there, and we have many interesting things going on and also interesting webinars. So today I'm going to talk a little bit about how digital forensics evolved in pretty much the last 20 years and why now artificial intelligence is so necessary to help us go forward. So a little bit about myself. As I said, I'm the coordinator of the Artificial Intelligence Lab. I work with AI and digital forensics for about 20 years, and I'm a professor at the University of Campinas for more than 13 years. And today I'm going to start with a very recent and complete definition of AI, and that's going to put us in the context of this talk. What is AI? So the definition here does not consider philosophy or the possibility of machines getting conscious or sentient, nothing of that. Our definition of AI is pretty much an engineering definition. So any system, any computer system, which has the ability to correctly interpret data from the world, learn from given problems, and use these learned capabilities to achieve specific objectives and tasks through flexible adaptation. So anything that you have that collect data from the world, analyze that data, interpret that data, learn from that data, and take decisions based on that data so that some actions can be performed and adapted over time. This is an algorithm in the realm of AI. And this is a very similar definition to digital forensics. So digital forensics, you can see that you can solve problems in digital forensics following a path according to the definition of AI. So this definition here is from my friend Edward Delp from Purdue University. So it's the collection of techniques for the acquisition, preservation, validation, identification, analysis, interpretation, documentation, presentation of digital evidence derived from digital sources for the purpose of facilitating or furthering the reconstruction of events, most of the times of criminal nature. So you can see that we have the data from the world. We need to preserve it. We need to validate it, identify it, analyze it, and interpret it, and then present it. So you can see that AI is pretty much present here and can be very useful because it will help us in terms of the acquisition, in terms of the preservation, mainly in terms of the analysis and identification, and then in the interpretation. So in this context, I'm going to talk a little bit about the fake news machine that we are living nowadays. And in this regard, I must say that about 10, 15 years ago, when we started heavily working with solutions for digital forensics for identifying forgeries, pretty much when we received an image like this, and in particular, this is a politician from the Netherlands, where Professor Zachariah Erkin is, we use it to rely on this image itself. So we would have only this image, and this would be the only piece of information or piece of evidence that we would have. And we would need to design signal processing techniques, computer vision techniques to help us analyze telltales to point out that this image was a fake. So which kind of telltales we would look for? Compression artifacts, acquisition artifacts, illumination, shadows, problems in terms of the texture, noise, all of this. These were like techniques based on signal processing and computer vision. And it works great. We have a pretty good deal of good techniques in the last like decade or so that were developed, and they are pretty good to help us analyze, particularly if a photograph is fake or not. But the problem is, the problems in digital forensics, they got more complicated. Now, instead of receiving one of these, or two or three in a week, we receive thousands. And we also have a key player entering this stage, which is artificial intelligence, helping to create these forgeries. And so we ask ourselves, is it possible to continue only dealing with these problems using signal processing and digital and computer vision techniques, looking at one signal at a time and one image at a time, one video at a time? No. So we needed to go one step forward. And in this regard, this is what I'm going to talk to you today, which is how can we ally digital forensics techniques that were developed over like the last 2 decades and AI to help us fight or counteract techniques creating forgeries using AI. So the examples that I'm going to show you, they are the result of several collaborations with many universities, and it goes in a project called Deja Vu. And this Deja Vu project is like a project in which it's an umbrella in our lab here in Recall AI, in which we investigate many digital forensics problems. And I'm going to give you some examples of the things that we have been doing and show you how AI is important in that sense. So I'm going to talk about fake news detection, which is a misleading term. Actually, is not fake news detection because it's a very, 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 did I say very, very difficult problem. It's more like fact checking and then detecting manipulations, authorship analysis, who is the author of a piece of text, especially a small piece of text like a tweet. Then person re-identification and space-time coherence. I'm going to give you some hints about each of these problems and show you how important AI is to help us. So let's start with an interesting problem called user agnostic motion profiling. This is not only forensics. This goes also for a new authentication technique. The idea here is it possible to help? Is it possible to detect if a person is the owner of a mobile phone by the way this person walks? This problem is known as gait recognition, and it has been studied for quite some time for images, for videos. So you have a video in the airport, and you try to identify a person by the way this person walks. So in that scenario, this is surveillance and monitoring, and it's not our focus here. Our focus is on the person, on the owner of the cell phone. Suppose that you are walking around and you are holding your phone close to your ear and someone comes and steals your phone. So we would like to have a mechanism in the phone that automatically locks the phone and does not allow this person to use your phone. And we are going to do that based on the pattern of walking. So if your cell phone is with you as the time goes by, the cell phone learns the way you walk. So the cell phone has a template of the form of your gait or the way that you walk. And from time to time, the cell phone checks if the person holding it is the person that's registered with that standard of walking. That's okay, because if you are the owner, you keep walking and the cell phone knows that you are you, and that's good. But if someone steals your phone, we would like the phone to, oh, hey, this is not my owner. So the standard, the gait pattern here is not the one that I learned. So this person is not the owner of the phone. So I'm going to lock the phone. So this is what we want to do. And this is what we wanted to do. This research we started like 5 years ago, and it's now concluded. It took a while to have the results, but the results are very interesting. We just had this research published in Nature. So if you are curious to see more about it, just check by my name, User Agnostic Motion Profiling at Nature. And you're going to see some of our research, and also in the Pattern Recognition Journal. So what we do, we get the signal from the cell phone, and we wanted to use standard hardware that's present in the phone. So we focus on the gyroscope, accelerometer, and magnetometer. And everything that we do to learn the behavior of a person walking, we just can use these 3 sensors, okay? But we also need to learn the patterns of the person over time. And when we started doing this, we wanted to do something that it would be visually possible to discern. So we transform all the signals into what we call hybrid images. So for each signal, which happens over time, we separate small windows. So a signal of accelerometer for like 1 minute. Then we get that 1 minute, and we transform that 1 minute into an image. And this technique is called the spectrogram. And we have different ways of transforming an image into a spectrogram that we proposed, especially for this problem, but it can have other applications. And the one that we did is, it goes like this. Typical images, they are represented in R, G, and B, which is a tensor of 3, right? So you have 3 matrices put together, so this forms an image. In our case, we extended this to have 6. So what are the 6? We have a representation for 1 person and 3 sensors, and then another person and 3 sensors. And then we can learn how different they are in terms of images. And if I'm of the same person, I have three sensors of John and 3 sensors of John, but in a different time, and then I can see the patterns of the same person. So I create this way of differentiating same user, different user in a tensor. So the input to our algorithm is a 6-channel tensor, the first 3 regarding the first person, and the second 3 regarding the same person or a different person. And this serves as a training. And we have different ways of creating these hybrid images. Once we have those hybrid images, we give them as input to a convolutional network look for patterns of the same person and then pieces of different people. And then as we analyze these data over time, we also can do combinations of the decisions over time. So we do what we call temporal coherence. And look, we are looking for the sensors of accelerometer, magnetometer, gyroscope. They generate a hybrid image. This hybrid image is the input of our network. Then the network trains to find the patterns of same person, different persons. Then we combine over time, and then in the end, we have the answer, same user and different user. So this algorithm runs in the mobile. So if someone comes in and steals your phone, the phone immediately knows that it's another person. Okay, so here's an example of the projection of our data. So we also collected a data set of more than 100 people in different days and wearing different clothes and different shoes to show the impact of these things. Here's the example for training and testing data. You can see that there is a shift. So this is a problem in machine learning called domain shift. And this is a problem in which we could not solve without machine learning, because how can I define the patterns to know that the person is the same person walking or not? So this is the first example in which AI is very, very important to help us solve, or machine learning in this particular scenario, which is a subfield of AI. So based on this information, we knew that we needed to go further in the problem to learn how a person walks, like in terms of biomechanics. And it was not sufficient to just use the sensors that we wanted, the way that we wanted. So we partnered with the University of McGill University in Canada, with a group of dancers. And with this group of dancers at the University of McGill, we collected a multi-sensor data set. We put in pretty much every joint of a person and accelerometer. And we wanted to know the patterns of walking. And the best group to learn the patterns of walking, of course, is the group of dancers. So we worked with like 25, 30 dancers. And we collected this data set with all of the sensors here and the best possible accelerometer that we could also get, which is the MCU. And we wanted to compare all of the joints signatures, and also we wanted to compare with the cell phone, and the cell phone is also with this person here. And based on that, we can collect all of the trajectories of these people in this stage, on this stage, and we could finally learn how biomechanics represent the walking. And doing that, we could collect the different trajectories. Here we have, like, for the different sensors, one is the FTC. For instance, if you go back, if you look at the signature, FTC, for instance, is on the waist, half of the body. We have one on the right and one on the left. So here you have FTC, FLE, and FAX. So each color here is a different person. Okay. Then we wanted now to, based on this kind of information, discover the frequencies that help us separate people. And pretty much everyone in the literature says that when you work with gait, you need to focus on the frequencies from 1 to 10 hertz. No, from 1 to 5 hertz. Everything happens from 1 to 5 hertz. And this was like a universal truth for gait. And based on this data set that we collected with dancers, we questioned this. Because if you focus on 1 to 5 hertz, you are looking for the size of the step, the strength that you put your feet back on the ground. You are looking at the acceleration, and this changes a lot. So if you change your shoes the next day, your standard of walking is going to be different. But the data sets available in the literature, they were limited in this regard. So we wanted to question this and to really find the frequencies that allowed us to separate people. And when we questioned that, we found it. And it's not from 1 to 5 hertz. The frequencies that allow us to separate one person to the other is from 6 to 10. It's not related to the size of the step. It's not related to the strength that you put your foot back on the ground. It's not related to the acceleration or how fast you walk. It's not related to the size of your step. You know what it's related to? It's related to the way that you swingle, the way that your waist moves. So when we focused on that, we could separate perfectly the groups. Here you can see the example. the group of same user and the group of different users. So same person, different person. You can see that these groups are pretty much separated in 2 dimensions. Imagine what we can do in any dimensions. And here is the visualization of the separation. Look the way that these people walk. The difference is on the waist. The difference is on the swing. So when you look a person walking, pay attention to the swing of this person, the way this person moves side to side. It's minimal, but each person has its own way of doing that. Look at the swing of the waist. This is what differentiates one person from the other. And this was not found in literature before. Here's another person. Look. So with this, we can separate people. We can detect who is the owner of the cell phone. It works great for some users, but there are some people that are very confusing. So it's not perfect. It's important to say that it will work with 95% for some users, most of the users, but there are some particular people that they have a very different way of walking, like a roboticized way, and we cannot differentiate them. So in our data set of like 100 people, there are like at least 8 or 10 that are very hard to discern. And this is nice also to discover. Okay, now shifting gears to a second problem. And this is like a very important problem that it's been overlooked until recently. And it became more apparent with the pandemic, which is the problem of forgeries, of falsification in science. So digital forensics is around for quite some years, and we have developed many important techniques for detecting if a natural image has been tampered with. But it turns out that some studies about images in science, they show that an astonishing percentage of the images are tampered with. Sometimes just to improve contrast or illumination, which is okay for some journals, as long as the authors make it clear. But sometimes with the clear intent of disinformation, of misguiding. And there is a study that shows that about 5% of the publications have some problems with their images. Of course, this 5% also count changes in contrast, but many times changes that were put there to deceive the viewer. So our focus here, this is a very big problem, very big project that we collaborate with several universities, University of Naples, University of Politecnico di Milano, University of Siena in Italy, and universities in the US like Purdue, Notre Dame, Southern California, Unicamp in Brazil. So it's a very big consortium to try to deal with this problem. And after like 4 years investigating, now we have an initial solution, which has been recently accepted at Nature, and will be published in 2 or 3 weeks probably. So here's an example. This is an image in science, and we focus now in biosciences. So this is an image of a result that they collect like in the microscope. And here's an example of an old problem in digital forensics, which is copy and paste. So copy and paste and contrast and illumination changes. So just to replicate the result, to have like more evidence of a good result, these authors like cloned the particular object of interest, and they put it in different orientations and different illumination. Then someone could come, hey, but couldn't we just use the techniques developed in the past decade in digital forensics to detect this? Yeah, we could try. And we did it, and they didn't work because these techniques were developed for natural images, and they were not developed aiming at these different sensors and this different imagery. So this is what we are working with now. We are trying to develop new techniques to deal with these problems like DNA gel, microscopy, and many other kinds of images that we have in biosciences, trying to find these forgeries. But this is not enough. So we created a whole pipeline to help us detect forgeries in publications. So we partnered with this group of researchers in Retraction Watch, and it's a website, and they maintain like thousands and thousands of retracted papers. So we partnered with them. We got their data to train our methods, and it goes like this: we building this pipeline in partnership with these universities that I mentioned, and funded by DARPA in the case of the other universities, and by the Research Foundation of São Paulo, FAPESP. We give the PDF of a paper. This is all you need to do. Just give me the PDF of a paper, and I extract all of the images of that PDF automatically. Then for each of the image, we decompose that image in the panel pieces, and we compare all of the panel pieces to a database of possible evidence. So we try to look for consistencies or inconsistencies in the image and between images. And then once we do that, we can point out if there is an example of copy and paste, which is inside the same image. We can find examples of splicing, which is the combination of different pieces of different images. We can find examples of reuse, people getting examples of old publications and just reusing them like with different illuminations or orientations. So we can do all of this. So we can detect forgeries intra and inter images, and we can also find patterns of reuse. And when we find the patterns of reuse, we want also to detect how it was reused over time. So we also create what we call Provenance Graph. So how the images evolved in the publications. So our idea, we are still going in that direction. Our idea is this. Suppose that you have a suspect paper. So you get that paper, you give us that paper. We extract the images and we do all of this pipeline, but we also get each of the authors' names, and we go online to get all of the papers for each of those authors, get all of this massive amount of data, extract all of the images of these papers, and we do this comparison here with all of the papers. Why? Because it's very common these authors reuse content from one another, creating what we call paper mills. It's not us that call it paper mills. It's an expression that exists in the area. So paper mills, they have pretty much two objectives. One, a group of authors unite and they want to boost citations from one another. So they keep citing each other. So this is not our objective. This is bad and unethical, but we don't work with this problem. We work with the other problem. When the authors get images from others and they modify them and put them to generate another paper. So this is a paper mill, one paper per day. So can we detect these paper mills? Yes. Some of them we can already detect. In our case, we could detect two until now. And we are writing a paper about this as we speak. This particular system here is the main result of our research so far, and it was just accepted in the Nature Scientific Reports. This is the paper that I was mentioning some minutes ago. So this is the second problem, that we could not deal with without machine learning. So you can see that we have examples here of signal processing. We have examples of computer vision, and we also have examples of the need of machine learning AI. So here's a third problem that I would like to discuss with you. So this problem is known in the literature as person re-identification. So suppose that there is a crime and a particular suspect is caught on camera in that particular XY position. So we would like to look over many other CCTVs and available cameras, which are in different positions, different angles, different viewpoints, different illumination background, and all of this. We wanted to identify the suspect in all of these different cameras so that we could have a more clear view of that particular suspect to have the possibility of identifying this person for criminal action. Turns out that most of the works in the literature, they consider supervised scenario to this, which is they have a data set, they have like 100 different people in this data set, and they know all the identities of the people in there. So if they are looking for John in this data set, for instance, identity 1 here, they compare this to the other 99 identities, and they know that there are other 99 identities in the data set. So they pretend to have the rest of the word, but they know there are other 99 identities. So this is a closed set scenario, a supervised scenario in which I know the labels of the other persons. In our case, we asked ourselves, is there anything I can do without having any kind of labels? So if I'm looking for this person in particular, this is my suspect. Suppose that I only have these 4 shots of identity 1 here. This is all I have. So using only these query images, can I go to a database of many different images? And these images can be of people, and they can be of anything else because I don't have labels. Can I go there and find the suspects? So this is the research that we have been doing for 3 years already, and only now we are getting the initial results. So research takes time. This is important for students to know. It takes time, but it's worth it. So in this case, we have changes in viewpoint, pose, illumination, occlusion, background, no labels at all. Okay, is it possible to identify the people? Yes, it is possible. So here is the result. This is like from the oven. It's not even published yet. We just put it in archive, so it's under review. We receive an ROI, a region of interest, which is a crop of an image. And we describe this crop, this image with different ways: standard, out of the shelf, convolutional neural networks. We don't train them. We just get them as is, and we call them backbones. So for each one of the networks that we use, we pass this image, we get the feature vector. So right now we are using three backbones, standard ones like ResNet and these networks that are trained over ImageNet. And then we combine these feature vectors just to have one. The idea here is that one network will be incapable of really representing the different people. So we get the different networks and then we average them out. So we have a more complete description of a person. Then we go to the main stage, the main step of our method, which is the clustering. Most of the techniques in the literature of re-ID, they try to do this clustering based on thresholds to decide if a particular feature point, a feature vector, belongs to a group. And most of the times, this clustering is what we call hard clustering. They decide if this point really belongs based on a threshold and done. The first thing that we did was, okay, what if I'm not sure about a point, if I should really put this point in this group. So we created this notion of I don't know and I don't care. So if a point comes in and I'm not sure if that point it belongs to a particular group, I just say, I don't know. And for this iteration, I don't care. So I paint this point as black. Perhaps this point in the next iteration will be part of a cluster, perhaps not. And it's not a problem. I'm not obliged to cluster all the points. What I need in the end is a good representation for each group, but a representation that I'm sure about. So this was the first change and contribution of our work. The second thing is, how can I decide if a point belongs to a particular group? Most of the works in the literature, as I said, they decide, is the distance of this guy to the guys in the group below a specific threshold? If yes, put it in the group. Or they try to do that like with a fraction in a probabilistic way. So this point belongs 40% to this group and 60% to another group, which would be a soft clustering. We did differently. We changed this in two ways. The first thing was, I'm only putting this point in this group if this point is also similar to the other neighbors of the points in the particular group. So I use context. So suppose that I want to decide if John, this image of John, belongs to this particular group. So for each point in this group, I get the neighbors. For instance, the 10 closest neighbors. So first guy in the group, 10 closest neighbors. Second guy in the group, 10 closest neighbors. Third guy in the group, 10 closest neighbors. So I have a list of neighbors for each person in the group. Now, I calculate the neighbors of this guy that I'm trying to see if it belongs to this group. So there must be an intersection in the list of neighbors, because if this guy is really from that group, it's similar to the persons in that group. So they must have pretty much the same friends, because friendship here is based on appearance. So we did this based on the context in a local way, but instead of just doing that in this particular iteration, I do that also over time. So this guy that belongs to a particular group, who were his friends in the first iteration, second iteration, third iteration, fourth iteration, and so on and so forth. So I keep a list of the neighbors based on the appearance. So neighbors are defined based on their appearance. And it seems that if the friendship is consistent over time, then this guy is really similar to the other. And now if I want to decide if a particular person belongs to that group, if I say that it belongs to that group because they share the same neighborhood, yeah, I'm pretty much sure that it belongs to that group. These two alterations, these two extensions allowed us to have a pretty good result in this problem, which is superior to recent papers in CVPR, even CVPR 2022, and solutions that consider supervised scenarios. So it's pretty good to see that it's possible to deal with this problem without labels. And we are trying to extend this to other problems. We did some experiments with authorship analysis, transforming texts into feature vectors, and from the feature vectors, everything looks similar, and the result is also equivalent. So in the paper we did for images and for text. So if you're curious to see, please take a look at the archive version of this. Reasoning for complex data with self-supervised learning. This is the title of the paper. Okay, so this was the third problem that I wanted to discuss with you. And in the end, you have XAI. So you can understand why a decision is taken. Here is the example of a person that I'm looking for, top left, and why a decision was taken. Like, this is a correct case because this person is holding a blue purse, wearing a blue shoes, and with a backpack. And what did the algorithm look at? Exactly these things. So this is a mechanism present in our algorithm, the explainability. And the failure case is also interesting. When we look at the cases that the algorithm failed, most of the times we have more than one person. Here is an example, 2 persons in the same region, and the algorithm, of course, is trained for 1 person. And you can see that there is a very interesting pattern. When the algorithm gets it wrong, it activates pretty much everything in the image. So you have this washed out, all green image instead of one that's blue with like redder regions in the most active areas. So now we are even thinking about putting a post-processing stage over these images to check if it was a failure case or a correct case. So here, this was the example of re-identification. Here's another problem for which it's pretty much impossible to deal with without machine learning. How to detect the author of a particular tweet or short message online in social media. And for these texts, we have normally 140 or 280 characters only. So what we do here, we try to identify the author of this particular message. In our case, a tweet. So we have, what are the challenges of this problem? We have a small sample size. Normally you have a few tweets for each author. You have ASCII and non-ASCII characters. You have misspelled words. Sometimes these misspelled words, they are intentional. Sometimes they are unintentional. We have internet jargon, onomatopoeias, hashtags. Here's an example. Hi, bro, wave hands. What's for tonight? Sunglasses. And this would be the tweet that we would need to analyze. And based on the stylistic forms of this particular author, our idea is to try to identify this author. So first thing, we transform the text into a signal. So we want to do everything with signal processing, of course. So we transform the text into a signal, and this was before transformers. So now it's possible to do this with these transformers available, BERT and others. We started doing this before transformers. So we transform the text into a signal, and then we don't care about normalization for case, don't care about stemming. We remove the too frequent words or too frequent grams because they don't help us to identify different authors, because if they are too frequent, they belong to different authors anyway. And we develop our own CNN to work with this, and we extend here based on the literature, the notion of pooling that we have in convolutional neural networks that normally select the best option each time. We select the k-best, so it's k-max pooling, because for text you have the notion of neighborhood. So to capture the context, we have this pooling which gets the k most important. And with this, we have an initial algorithm for attributing the author for a short message. And recently, we also extended this to incorporate explainability to point out in the text which were the pieces that helped me to attribute that message to a particular author. So what's the stylistic form present in this text that helped me to attribute the message? So for that, we use a technique called LIME, which was proposed by another team, and it highlights the pieces of text that help us to show the parts used for attribution. This is present in a recent paper of ours, if you're curious. This is IEEE ICAST 2022, so very recent. These are initial results with some PhDs of mine and a collaborator, Fernanda from LEGO. And here are the results. When we consider like the explanations, right now we have an attribution rate of 89% for a data set with 50 authors each time. 50 suspects, 50. All right. So I think that to have time for questions, I'm gonna skip this one about fake news because it's a common subject. If you're curious to see more about this, I can comment later. But I'm gonna give you one more example as we have 15 minutes. So in 2-3 minutes, I'm gonna give you one more example, which is this one. For many years, it's a standard belief in forensics that EXIF information, information that's present in the header of an image can be easily modified, and this is true. And it's also true that it was pretty much difficult to see that someone did it. So here's an example of a work that I did with collaborators, and mainly this work was done by a PhD student of mine, a former PhD, now a doctor, Raphael. We wanted to compare the content of an image to see if it was consistent or not with the timestamp. And we know examples that they change timestamps or they change the content, like the Ukraine war is an example, just the latest. So here's an example. So this top image, September 7 a.m. North Hemisphere, is it consistent? Yeah, September 7 a.m. Okay. But the one on the bottom, March 10 a.m. South Hemisphere, it must be inconsistent. So can we detect this automatically based on the content and comparing the content to the timestamp? So this is what we did. Given an image, we extract its alleged timestamp and geolocation, and we give them as input to our algorithm. And we also get the satellite image associated with that particular ground image. And this network is trained to check if the photograph matches the timestamp or not. So this is the top part of the network, which is a binary classifier. And the bottom part deals with explainable attributes, because we want to understand why a decision is taken. So for each image, we match the ground and the satellite, the alleged timestamp, the alleged geolocation, and we try to see consistency or inconsistency. And we trained this with thousands and thousands of examples from CCTV cameras from the world. And in the end, we have some interesting results. So here's an example. On the left, you have a ground image, and it's an aerial view. And our method can estimate the time of the day that it was taken. And the comparison, the baseline is from CPR 2020, and you can see that our algorithm is much more well constrained. In the middle, you can see an image that's taken at nighttime, and its version aerial. And we can see that we could estimate the time between 9 and 11 p.m. And the baseline here was like between 7 and 7 p.m. So a very large interval. So this is not solved, of course. There are a lot of problems to deal with yet, but this is the first step, trying to check if the timestamp is consistent with the information, visual information present in an image. So to close, I would like to discuss the challenges of the area. So we need to develop solutions that are adaptable over time. So we need to do continuous learning. The conditions are dynamic. We need to incorporate explanation. We need to deal with biases. We know that we cannot assume that we know everything. So these solutions need to be capable of doing open set recognition. Sometimes we deal with different sensors, time series, audio, images, videos, volumes, text, and everything. So these are the heterogeneous sensors. Sometimes we have big data, sometimes just a few examples. Sometimes the sensors fail. Sometimes we have lack of data. So all of these are challenges for us. And this is what motivates us to keep going forward. We want to open the Pandora box, develop algorithms that are intelligible, that are auditable, fair, ethical, And with that, I would like to thank you all for your attention. We have some minutes for questions, and thanks a lot.
Thank you very much, Professor Rocha and Anderson. So really nice presentation. I can see one question in the Q&A part. If you take a look, do you see that?
Yes.
Okay.
Rob, a general remark. In court, since two different people might potentially have very similar gait, introducing such evidence is in a legal proceeding would need to be combined with a scientific statement of likelihood. The concern is that an advocate will say, we use the computer and AI, and the court will then give the information greater weight, even though there is significant uncertainty. For sure, Rob, you are right about this. That's why I mentioned in the beginning, we are not using this for the court. We are using this particularly to block the cell phone from someone trying to use your cell phone without being the owner. Okay, but if we ever want to develop this, like in terms of the airports or something to use in court, we need to have a whole deal of other things to complement the approach.
Great. For our participants, if you have questions, please either type it in or just go ahead and ask your question directly. Anderson, I'm a privacy researcher, so privacy is very important, and I use crypto for this. Even though your research is very valuable for security in general, there's also a privacy threat, right, for surveillance purposes. What do you think about that?
Well, I knew that you would ask something about that. Well, first thing, I do the research and you do the counter research. No, it's important. We need to consider the security and the privacy concerns. And one area that's growing a lot recently is federated learning. So you can do the learning without sharing the data, and you can do that on the device or on the edge, as they say. And you can share only the weights of your solution, the parameters, or things like that. But in particular, I'm guessing that you're talking about the re-ID. So the re-ID for us was not particularly chosen because it was like a re-ID. We chose a problem in that case because we wanted something that was very hard in terms of illumination changes, poses, and viewpoints and everything, because our aim in that case was, can I work without labels? So for us, any kind of problem in that case would work. And indeed we did for authorship later on. But the re-ID itself has two sides, right? It can be used for good. If something happens like a terrorist attack or something, or in a big football game, we have like gangs fighting each other. So you could use the re-ID to help you. But we also have examples of countries misusing that kind of technology. And one recent example that I read in an article called AI Colonization, pretty good series from MIT Technology Review, and they gave an example of South Africa. So in South Africa recently, they are putting like in pretty much every corner one of these smart cameras to know what's going on. So I have this concern as well. And I think that we should think about it. Yeah. There is no solution right now to deal with that without like policies, like protection policies.
Yeah, but this is a common problem for any domain, not only GATE. At the moment, I'm in Dachstuhl for a speech and language technology seminar, and the privacy and security are the core problems. How can we protect people? But as you said, it's just
federated learning is the main field right now that I believe can help us.
Exactly. So we will be busy for the upcoming decades, I believe, with this topic as well. I'm looking at the participants. Is there any urgent burning question for Professor Rocha? If not, I really want to thank you, Anderson, once again. Just after the summer break, you reserved your time for this really beautiful talk. For your information, it's live stream on YouTube, but it will be also recorded and it will be added to the list of SPS webinar series. And possibly I will send the link to you as well. Everyone, thank you very much for being here. It was a really nice afternoon from the perspective of Europeans here. It's really warm, 30 degrees. It's unusual. And I will see you in September for the next webinar. Have a nice day, have a nice evening, wherever you are on Earth. For now, goodbye. Thank you very much for everything.
Goodbye. Thank you. Bye-bye.